So this is a lightning review of the harmonic oscillator, which takes this form. Hamiltonian operator is p squared by twice m plus half m omega squared x squared. Exactly the classical form quantized for in general. And in the position picture, we know that p can be replaced by this differential operator, and the Hamiltonian operator looks like minus h cross square by twice m del 2 del x2 plus half m omega square x square, where the operator for x in the position picture is just multiply by x. So if we now introduce the lowering and raising operators, which are basically x plus ip by m omega and x minus ip by m omega, apart from two factors which are chosen essentially to ensure that the commutator bracket of A and A dagger is 1, we end up with this Hamiltonian, which now becomes h cross omega A dagger A plus half. And A dagger A is our favorite number operator. As we will see, it's called the number operator because it can only have eigenvalues which are natural numbers. This form, of course, implies that any eigenstate of number operator is also an eigenstate of the Hamiltonian. So if n acting on a state ket n gives you n times ket n. Again, if you're not familiar with the bracket notation, just substitute psi n for ket n. Then Hamiltonian acting on the same ket n will be h cross omega n plus half ket n. So if you know the eigenvalues for capital N, you know the eigenvalues for the Hamiltonian. Now, the most important result for us is that the commutator brackets of n with A and A dagger are very, very simple. That of n with A is minus A, and n with A dagger is plus A dagger. And it is this property which allows you to conclude that if A, the operator, were to act on an eigenket of n with eigenvalues n, it is going to reduce the eigenvalue by 1. And A dagger similarly is going to raise the eigenvalue by 1. And I'm pretty sure all of you are, or at least most of you have seen these equations, that A acting on ket n gives you ket n minus 1, and A dagger acting on ket n gives you ket n plus 1. These are normalization factors which ensure that both ket n and ket n minus 1, or ket n plus 1 as the case may be, end up being normalized to unity. Now, the important thing is, if I keep on hitting an eigenstate with A, the eigenvalue n goes down by 1 every time. But the Hamiltonian H, being the sum of two squares of Hermitian operators, p square and x square, with positive coefficients, must have only positive eigenvalues. And that means that this lowering cannot continue forever. It must be bounded below. And the only way this can be bounded below is that there must be a state, which I'm going to call ket 0, on which the operator A acts and gives you 0 and not a new eigenstate, not an eigenstate corresponding to eigenvalue minus 1. And once you have this, from this state, you should be able to get to any eigenstate by keeping on applying A dagger. And that tells you that the possible values for the eigenvalues of capital N must be non-negative integers, 0, 1, 2, 3, and so on. And this is one result that we are going to need. If you just keep on applying A dagger on the state 0, you get A dagger acting on ket 0 once to be ket 1. Then A dagger acting on ket 1 gives you ket 2 by root 2 and so on. If you just repeat that small n times, you end up with the ket n being A dagger raised to ket n to the power n by square root of n factorial, this operator acting on ket 0.